It's very easy to forget when designing or modeling using Zebra or any other software that a lot of things are interlinked within a building. So it's not really a question of getting the energy use of the building as low as possible and then thinking about the acoustics, for example. The two are related. And they're more than just related, they are deeply interlinked. So if we give one example, thermal mass. You can use thermal mass to control the peak time temperature within the building by storing heat or coolth. But you usually use that by exposing stone, brick, concrete, steel, oak beams, something to store that heat in to the temperature within the room. And if you do that, you'll find that those surfaces are very reflective of sound. So the reverberation time, the echoiness of the space, will go up the more you expose the thermal mass. And conversely, if you decide to use soft finishes to mop up the sound, things like carpets, maybe drywall systems and things like that, punctuated plasterboard, mineral wool, then you will reduce the thermal mass. So you won't be able to store that coolth. So not only have you got to be able to think of all the different ways that the physics of a building is expressed, but you've also got to remember how interlinked they are. And we can describe this as inter-issue design or holistic design, or any other term you like, really. But the main thing is to remember it's not just a question of getting each physics problem solved one at a time, but the fact that if you solve one in one way, then it's likely to cause an issue with the next one. So let's just start with beauty. There you go. If you think about what your building looks like, the volumes of the rooms, the volume of the space is one of the parameters in the equation which defines the reverberation time, the echoiness of the space. The volume of the space will have an impact on air quality within that space. Okay, surface finishes, as I just said, have an impact as well. But shape, a curve, can look very nice, but it can also focus sound and cause some form of strange echo effect that you may not want to achieve and probably don't actually want to achieve. So really think about how one thing impacts the other. Don't optimize for one thing and then try and optimize for the next thing on the list. You've got to somehow juggle and hold within your head whilst you're sketching or just thinking about a building, all these things. So let's just go through a few of them. So we've got beauty as the first one, and this is in no particular order. Then humidity. How are you going to dehumidify the air if you need to? Can you moisture buffer the air within certain materials, bio-based materials that absorb? And if you do, how will that impact heat storage, coolth storage, reverberation, etc.? Water ingress into the insulation layer or into the building in general. You're going to end up using certain finishes that'll have an impact on maybe the embodied energy of the building, which you might also be trying to minimize. Okay, condensation, cold points. You're going to have to use certain construction techniques to avoid condensation, and again that will have an impact. If you use triple glazing to avoid condensation on the windows, you've got 3 times as much glass. So in which case you've got 3 times, very roughly, the embodied energy of the glass. So it's deeply interlinked. You're trying to optimize, maybe minimize use of materials, but optimize the situation, but it's all interlinked. Security, window opening, to provide temperatures in bedrooms at night on the ground floor. If you've got ground floor bedrooms, you may want to be having the windows open, but if you have the windows open, there's a security risk. So can you provide opportunities for other ways for air to enter the building? And if you do that, are there issues with those? For example, in the UK, if you start bringing in air through complicated ductwork, you can get mold growth, condensation, etc. What about optimizing the carbon footprint of the building. That's very easy to think about that in terms of operational energy use, heating, cooling, embodied energy, so the energy and carbon footprint of the materials and transportation and construction and everything else. But another way to think about the problem is carbon in terms of the hours of use. So you could put a building together that has a certain carbon footprint. You can measure that in kilograms of CO2 equivalent. But what really matters in a sense is the amount of economic benefit or benefit to people or society that you get from the expenditure of that amount of carbon. So maybe a better way of dealing with the situation is a slightly higher carbon footprint for the building, but doubling the number of hours of use of the building due to the fact it fulfills more than one role. It could be a school during the day, but then at the weekend it could be some kind of sports facility or something else. And in a sense, because that's avoiding another facility being built, you are reducing the total carbon expenditure from your society. So, some really stuff that you don't normally think about in architectural terms or structural engineering terms or material terms or energy efficiency terms all have to be thought about to try and provide the best building possible on all these different axes, all these different bits of physics and economics and realities. Okay, longevity. Maybe you don't want the minimum carbon emissions from the building. If you can make a building that's going to last 4 times longer and you believe it will stand for 4 times the length of time and won't be redeveloped. So slightly higher carbon emissions might be allowable. And that might suggest different materials can be used or should be used. Maybe more concrete, which you might have been trying to stay away from because it has a huge carbon footprint. Air quality would be a classic example. If your building's in a polluted situation, then where you place the openings or where you bring the air in or the system that you use to bring the air in rather than natural ventilation, possibly because you might need filters, it's greatly impacted by the environment the building is sitting in. The room I'm sitting here, the building I'm sitting in at the moment, you can probably see out the window, it's a rural setting. Air quality is not really an issue, and I can just open that window and provide as much ventilation as I like. Well, that wouldn't be necessarily true in a city setting, and I may want to use a different system. But if I use a different system, so I use a mechanically drawn system, the fans are going to produce some noise. So where do I site the fan? I've got to leave room for the fan, but I've also got to think about the impact of the fan on maybe a bedroom environment, and will it be too noisy? But on the other hand, in an urban environment, maybe it'll actually be quieter than opening the window because of the road noise. So it's all beautifully, in a sense of it's either beautifully or annoyingly connected. If you like this idea of multi-criteria inter-issue design and buildings being this holistic thing, it's fantastic. And if you like lots of physics, it's fantastic as well. But if you want to go down a line of we're going to optimize that, and then we're going to optimize that, and then we're going to optimize that, well, you're not going to end up with a very good building. So whenever you're just going to keep emphasizing, whenever you're designing, whenever you've got the pencils out, or whenever you're modeling and you're kind of adjusting parameters in the model, so you're in Zebra or you're in some other software, and you're going to increase the size of the windows to let extra daylight in. Well, think about the fact that you increase the size of the window. Windows are normally not very good at keeping sound out, even when they're closed. They're not ideal. So you're letting more sound into the building. So, got a problem. We need softer finishes. So let's have softer finishes to mop up that extra sound. Excellent idea. But then we've removed the thermal mass. And you need to learn tricks to kind of get around that situation. So a common way of mopping up sound in a space, which doesn't involve changing the thermal mass of the surfaces, is to use hanging baffles. Now, they're very suitable in a restaurant, in a cafe, in an industrial setting, in a swimming pool, a whole load of settings like that, not so suitable in the home. So think about the aesthetics, think about the impact of using hanging baffles on the beauty of your building, for example. Often you can be helped by thinking about the problem in a series of ways and finding a way through this pyramid of inter-issue design by considering different ways of actually approaching the problem. So an example would be cooling. You can straightforward adopt air conditioning. But if you do that, you might get into problems of where are we going to put the kit, noise, etc. So you may say, oh, I wonder if we can just use adaptive comfort theory and avoid the need for cooling at all. And that will involve talking to the clients, the potential occupants, doing some human-based work to find out the best way to navigate this inter-issue design problem. Think about acoustics. So think about the reverberation time of your space. One impact of that one parameter that goes into that is the surface finishes. Another one, as I said, is the volume. So think about what the space will sound like. And you can get software actually that will allow you to play through your headphones what the space will sound like if you have a violin in it, if you have people talking in it, if you have machines in it. And listen to that. And although you'll produce numbers for the reverberation time and how loud the noise is, listen, actually get a really good idea of what it sounds like, and maybe play that to the potential occupants or the client and say, is this what you want? This is the level, this is what 35 dB of sound transmission through a wall would sound like, how noisy it is. You know, this is how much of the English class you'll be able to hear in the maths class that's next door. And you can present that as a number, but those numbers don't mean things to most people. In fact, they don't mean that much to architects really either. Same as daylighting. I've got a lot of daylight coming through this window at the moment. That's absolutely fantastic. But as an architect or an building engineer or a modeler, you need to understand how much, what 300 lux on the working plane actually looks. How much light do I have in this room at the moment? So if your software model produces a certain number of lux, what does that feel like to be? What kind of atmosphere? Does that give a soft, romantic, nighttime feel to a space? Or is it dark and dingy? Or is it too bright and more like an operating theatre? You've got to get a real visceral idea of the relationship between numbers and emotions. So we're not only dealing with this multi-issue design space in terms of numeric values, reverberation times, etc., but we're dealing with it in an emotive way. So reducing the carbon footprint of your building would lead to a different building, and therefore it'll lead to a different emotional state for the occupants. So think people, don't just think physics. How are you going to light the space in general anyway? Are you going to use ceiling mounted spotlights? Are you going to drill holes in the ceiling? Well, if there's a floor above, sound transmission is obviously going to be a problem, and you're going to have to resolve that with some detailing. And that detailing can be expensive to implement on site. It can be, you'll spend a lot more time boxing in those spotlights than just plasterboarding the ceiling in the first place. So that's an issue. And if the budget is limited, what are you going to strip out? More insulation in, some of your insulation in the walls. So interlinked. Natural lighting. If you look at the window here, where's the light actually coming in? Okay, and actually, hopefully this will be picked up quite nicely on this recording, that virtually all of the light coming into this room, despite the big window, is not coming in through the big window, it's coming in through the top quarter of that window. So that's critical. If you started putting a shading element on that top window head, that's exactly the daylight you'd interact with, and you get a lot darker in here. You might think you could just make this window smaller, okay, to reduce the heat loss. Very sensible idea. It's quite a large window, and there's several of them in this room. But which bit of the window you're going to remove? You're going to make the windows thinner, or you're going to make them not so tall? And if you're not going to make them so tall, are you going to knock off the bottom, or are you going to knock off the top? And that'll have an impact on the lighting. Heat loss wise, it'll have the same it won't make any difference as long as you remove the same area of glass. Okay. Another area it will have an impact on is solar gain, of course, which if this room gets too hot, it could be really good to reduce light coming in the top of the window, because that's where your sunlight's probably going to come in from. But that's reducing the hours that this room can be lit naturally. So we're going to have to increase the amount of artificial lighting use. Now, these days, that's less of a problem, as it turns out, because we have very efficient LED lighting systems. They don't introduce very much heat into the space, and they don't have much of a carbon impact either, because they use very little electricity. So things are changing with time. Technology is changing. Fans are becoming quieter, etc. So whenever modeling or just getting the pencils out or sketching on the computer, please think about holistic or inter-issue design, and remember it's not a question of ticking each one in turn. It's holding them all balanced in your head, or it's like a set of spinning plates on poles, or juggling balls. Okay, you've got to keep it all in your head and remember the people. Thank you very much.